Jai Hind everyone, I am Dr. Nitisha Srivastav, faculty in the Department of Electrical and Electronics Engineering, Ajay Kumar Garg Engineering College, Ghaziabad, Uttar Pradesh in India. So this is in continuation to the root locus lecture series. This is the second lecture. In this lecture, we will understand the basic properties of root locus, basic properties to plot the root locus. As we discussed, the root locus is a graphical method for analysis of a system to determine the stability, to determine the transient response of the system for a varying parameter which is changing in the control system. So we will discuss here the basic properties starting from property 1 to property 5. So here it is root locus is a graphical method in which roots of the characteristic equation are plotted in S-plane for different values of the parameter. So what is a characteristic equation? Now this is the transfer function of a closed loop system. GS is the forward path transfer function, HS is the feedback, and therefore the closed loop system is GS upon 1 plus GSHS. So the open loop gain parameter K is considered variable when drawing the root locus of the system. As discussed, like one example we had taken that the fuel of the aircraft during takeoff and during landing is not the same. So that is one mass which is changing. So we can consider that as the changing parameter K. So the open loop gain parameter K is considered variable for drawing the root locus of a system. So again we can understand the locus of the roots of the characteristic equation when the gain is varied from 0 to infinity is called the root locus. We'll start with the first property. The rule 1 states that since you are varying the parameter, so we will start with K equal to 0. So always the root loci originates from an open loop pole with K equal to 0. Now consider this closed loop system as we had mentioned KGS upon 1 plus KGS. We can see that it is influencing the location of the poles. So GSHS can be written as minus 1 by K. This characteristic equation, since we are talking about the open loop pole with K equal to 0. So GSHS is known as the open loop transfer function or forward path transfer function. Now as the magnitude of K approaches 0, it is having certain value, but as the magnitude of K approaches 0, it means that this GSHS approaches infinity. So when can this GSHS approach infinity? It is only when S must approach the poles of GSHS. Only then this value becomes infinite. Okay? The rule 2 states that because the open loop transfer function is originating, it's starting from K equal to 0. And the second rule is where is that root locus moving after that? After once it has started from K equal to 0, where is the root locus moving? So it will terminate somewhere. So where it is terminating, it will terminate either on a open loop 0 or it will terminate at infinity. Terminate at infinity means there is some pole at infinity where it is going and terminating, right? So the root loci terminates either on an open loop 0 or infinity. Okay. So if the root locus is starting, if this is the location of the poles, then, and if you have a 0 here, then one of the root locus or one of the branch will terminate in a 0, whereas the other will approach infinity. Now, the root loci terminates either on an open loop 0 or infinity. The number of branches terminating on infinity equals the number of open loop poles minus 0. Now, if there are 2 poles and 1 zeros in the system, then as said, one root locus, one branch will start at the open loop pole and terminate at the 0, whereas the other will terminate at infinity. So, how many branches are there? That determines, that can be determined by knowing the number of poles and the number of zeros, that is P minus Z, which are terminating at infinity. So that is P minus Z. Now consider this closed loop system here, and the characteristic equation is 1 plus K GSHS equal to 0. Therefore, GSHS is equal to minus 1 by K. GSHS is known as the open loop transfer function or the forward path transfer function. Now we are talking about where would the root locus terminate. So we are talking about this plus or minus infinity of the K. So root locus starts at an when K is equal to 0 at an open loop pole and terminates at K is equal to plus or minus infinity. So as the magnitude of K approaches infinity, then GSHS approaches 0. Therefore, the S must approach zeros of GSHS. Right? But where we are talking about the poles, as magnitude K approaches 0, GSHS approaches infinity and S must approach the poles. But in case of this, as the magnitude K approaches infinity, GSHS approaches 0. So, S must approach zeros of GSHS. So, let us look here. When S is equal to, this is the condition, right? So, when K is equal to 0, what do you mean by K is equal to 0 here? K is equal to 0 means this part should be infinite, that is S plus 5 upon when S is equal to the pole, when S is approaching the pole, that is minus 3 plus 3, which is S plus 5 equal to 0, right? And then when is this possible? And then when S is equal to minus 5, that is when S approaches the 0, then this becomes 0 upon S plus 3. So, the second, that is the case when S must approach zeros of GSHS. So, what is the third rule? Third rule is number of branches of root loci. How many branches are there? In the previous one, we understood that how many branches are going to infinity, which root locuses are going to infinity. And whereas in this, we will know how many branches of root loci are there. The number of branches of the root loci is equal to the order of the polynomial of the characteristic equation. So, what is the order of the characteristic equation? Represents the poles of the transfer function, right? This represents the poles of the transfer function. So, as the number of poles are there, that many branches will be there of the root locus. So, GSHS here is the open loop transfer function or the forward path transfer function. A branch of the root loci is the locus of one root when K varies from minus infinity to plus infinity. So, how many branches are there? For example, we have 3 poles. So, there would be 3 branches because because there are 3 poles. Each root locus will originate from the pole and terminate at an open loop 0 or terminate at infinity, starting from k equal to 0. So, branch means what? Branch means locus of one root when k varies from 0 to infinity. So, let p be the number of poles and z be the number of zeros. So, how many separate loci you will get? That is n. What would be the value of n? If p is equal to z, then n is equal to p, which is equal to z. If number of poles and number of zeros are same, then the number of loci will be equal to p equal to z. If poles are greater than zeros, then it is that number of loci will be equal to number of poles. In case the zeros are greater than poles, then number of loci will be equal to the number of zeros. Therefore, as said, the number of branches of the root loci is equal to the order of the polynomial of the characteristic equation. Basic property of root locus, rule number 4. Rule number 4 says that the root loci is symmetrical about the real axis. The root locus is symmetrical about the real axis. For example, if you have a root locus which is starting from here and there is a pole over here also, there is some breakaway point, then if this is going towards infinity, the other one will come down. Or if you have a root locus of this kind, then root locus starting from here going towards infinity, there is another root locus starting from here and going towards the infinity. So, root locus is symmetrical about the real axis. In general, root loci is symmetrical with respect to axis of symmetry of the pole 0 configuration. This is because of real coefficients of the characteristic equation. The root must be either real or in the complex conjugate pair. Like roots will, if they are complex poles, then definitely they will be in complex conjugate pair. Rule number 5. Let us see what is rule number 5. So, rule number 5 lets us know where on the real axis will be the root loci. This can be any point on the real axis is a part of root locus if and only if the number of poles plus zeros to its right is odd, right? So, this rule lets us know which part of the real axis is part of root locus. For example, let us plot this. What it will be? There are 3 poles, one at 0, -4 and -5. So, let us say there is one pole here. This is say -4 and -5. Now, which part on the real axis would be the part of root locus? So, it clearly states that any point on real axis is a part of the root locus if and only if the number of poles plus zeros to its right is odd. So, now at this point we can see that number of poles to its right is how much? 1. There is one pole on the right. So, this part on the real axis is part of root locus. But as you move to the left of -4, the region between -4 and -5, it can be seen that when you look from this side, from this point, when you look from this point, you can see that the number of poles plus number of zeros to the right side is an even number. So this part between -5 and -4 is not part of root locus. But when you move towards this side, that is -5, when you look at this side from here, the number of poles plus number of zeros of the system to the right side is an odd number, 1, 2 and 3. Therefore, this part is part of the root locus. So, this property lets us know that which part on the real axis is part of the root locus. So, this is what we covered, the basic properties from property 1 to property 5 in second lecture. The other properties will be covered in the future lectures. Thank you very much.